Welcome to the course Compiler Design. In this lecture, we will start the last phase of compiler. So that is code generator. So this is the sixth phase of compiler. So as part of code generator, the following are various topics. First, we will discuss various issues in the design of a code generator. Then the target language, addresses in the target code, basic blocks and flow graphs, optimization of basic blocks, a simple code generator, people optimization, register allocation and assignment, dynamic programming, code generation. These are all the various topics we're going to cover under the code generation phase. So here, code optimization techniques also included here. See, the people optimization is one of the code optimization technique. So that is the fifth phase of compiler. So this technique will be covered in code generation itself. Then in last chapter, other code optimization techniques are covered. Now let us come to the first, what is the role of code generator in the phases of compiler? So every phase we are seeing the role of or the position of a phase in the compilation model. Now the following diagram shows position of code generator. So first we are having source program as the input, then front end. What front end contains? Lexical analysis, syntax analysis, then semantic analysis. So these phases comes under front end. So followed by intermediate code. So then after front end, what we are having? Code optimizer, then code generator. Code optimizer and code generator, which are in backend. So backend pages, so that is code optimizer. So code optimizer is an optional phase. Then code generator. These are all the backend pages. These backend pages produces the target code, which is our required output. Now you can see after front end, so we already know what is the output of front end. That means semantic analysis output. So that is valid syntax constructs for abstract syntax tree obtained from syntax analysis. That is the output of semantic analysis by applying type checking or type conversion. Then those can be taken as input to the intermediate code, then represented into intermediate representation like syntax tree or three address code like quadruple, triple, indirect triple, etc. So that is the output of intermediate code. Then intermediate code, whatever the code obtained in the form of three address code, that can be optimized by using code optimizer. So then again you will get the same intermediate code only, but with optimized. So here what we will get? Optimized intermediate code. Now the optimized code can be taken as input to the code generator, that is the last phase, then produces the target code. Now we are discussing about code generator. So this is the role of code generator in the phases of compilation model. Now for code generator, whatever the output we are producing, what are the requirements here? Output code must be correct. Whatever the output code we are producing, that should be correct. Then output code must be of high quality. So that means high quality means which gives the good results. The code should be in the optimized form, so which gives the efficient results. The code generator should run efficiently. So these are all the requirements of the target code. Output code must be correct. Output code must be of high quality. The code generator should run efficiently. This is the position of code generator in the phases of compilation model. Now, as part of code generator, the first topic, issues in the design of code generator. While designing a code generator, what are the issues or factors needs to be considered? The first issue or the first design factor is input to the code generator. So what is the input to the code generator? Output of code optimization, that is optimized intermediate code. So intermediate representation. So this can be termed as IR with a symbol table. So assume that the input has been validated by front end. By front end means up to the semantic analysis, then intermediate code output. So that is the printed. There are several choices for the intermediate language, including the first one is linear representation, such as postfix notation, three address representation, such as quadruples, then virtual machine representation, such as stack machine code, and graphical representation, such as syntax trees and DAGs, that is directed acyclic graphs. So these are all various intermediate representations. So we covered the postfix notation, three address representation, quadruples. So then graphical representation, syntax tree, DAG. All these representations we discussed during intermediate code generation. So these are all the input to the code generator and various representation. Then the second design issue, target program. The target program is nothing but the output. So now the output of the code generator is the target program. So like intermediate code, this output may take on a variety of forms. What are the various forms of target program or output code in the code generator? The first one is absolute machine language. So which is fast for small programs. Then relocatable machine language. It requires linkers and loaders. These are all the cousins of the compiler. Cousins of compiler. So we discussed during the first unit, introduction to compilers, loaders and linkers. Then assembly language requires assembler, linker and loader. See, in the phases of compiler we already covered. So output of the code generator, directly we can't get machine language. So we will obtain assembly language. So then that assembly language is converted into machine language by using assembler. Then that can be linked, that can be loaded, so into memory. So that's why these are all the various forms of the output of the code generator. So absolute machine language, it is fast for small programs. Relocatable machine language, which requires linker and loader. Then assembly language requires assembler, linker, loader. That is the second design issue of code generator. Then third one, memory management. So the third design issue is memory management. So mapping names in the source program to addresses of data objects during runtime memory. So how this can be done in runtime memory. So mapping names, whatever the variable names in the source program, map to addresses of data objects in runtime memory is done. So is done cooperatively by the front end and the code generator. So then if machine code is being generated, then labels in the three address statements have to be converted to address of instruction. This is the memory management. So mapping names in the source program to addresses of data objects in runtime memory is done cooperatively by the front end and the code generator. If machine code is being generated, then labels in the three address statements have to be converted to the addresses of instructions. That is the memory management. Then the fourth design issue is instruction selection. Instruction selection. So here choosing appropriate target mission instructions to implement the intermediate representation statements. So here some important factors are during instruction selection. We need to consider uniformity, then completeness, then instructions speed and power consumption. So these factors needs to be considered during instruction selection. So here the complexity of mapping intermediate representation program into code sequence for the target mission depends on the following. First one is the level of intermediate representation, which is high level to low level. Then nature of instruction set, that is data type support. Then desired quality of generated code depends on speed and size. So these are all the various factors where the complexity of mapping intermediate representation into code sequence for target mission depends on this. So let us consider one example here. The sequence of statements. So here A equal to B plus C, D equal to A plus E. What are these statements? These are all three address statements. So we know what is the general form of three address statements. A equal to B, O, P, C. Here OP is the operator, B and C are the operands, then A is the result. So here B and C two results, then A one result, total three addresses. Now this can be translated into these three other statements: A equal to B plus C, D equal to A plus E, translated into the following code. What is this code? This is nothing but assembly language. Assembly language code. So in computer architecture and organization, you studied so about this instructions and the conversion of the code into assembly language code. So now in the code generator also, we will generate this assembly code. Then using assembler from here, using assembler, the assembly language is converted into machine level language. So which is the output, that is our target. So target language for the code generator. First we will generate assembly language code by using assembler. Assembly language code is converted into machine language. That is our final outcome of the code generation. Now for these two three-headed statements, see how the assembly language code is given here. See, first B plus C, we are moving the operand value B into register R0. So move B comma R0. Now what R0 contains? B. Now for that C is added. So add C comma R0. So now first one is over. Then what you have to do? Move this result to A. So now R0 what contains? B plus C. So you have to move that R0 to A. Now here this is nothing but A equal to B plus C. Similarly, the second part D equal to A plus E. So now again here you have to move A to a register R0. So move A comma R0. So now here R0 contains A. Then you have to add E to R0. Then add E comma R0. So then moving A plus E to D0. Now what R0 contains? A plus E. That can be moved to D0. Now here I mean D equal to A plus E. So this is one form of assembly language program code. So what it contains? Set of instructions or mnemonics, then followed by operands with registers or with the constants or with pointers, etc. So this is one example of assembly language code that can be obtained from the sequence of three address statements. So the code generator output is this one, a simple code generator algorithm that we will discuss in due of the code generator. So after discussion of that algorithm, how to write this code and how to find the cost of each and every instruction will be covered. Okay, now here you can observe the fourth statement. What is the fourth statement? Move A comma R0. Move A comma R0 is redundant. So why? Because here move A comma R0, then previous one move R0 comma A. So here same register, same operand value. So and so the third, if A is not subsequently used. So this statement fourth one, move A comma R0, can be eliminated by introducing increment instruction denoted as INC. Incremented instructions, capital INC. Then the three address statement A equal to A plus 1 may be implemented more efficiently by the single instruction with INC A. INC A is nothing but what it gives? A equal to A plus 1 rather than using move A comma R0. So in this, by introducing increment instruction, so one instruction, redundant instruction may be eliminated. Then the code is optimized. You will get efficient code. Now let us see that will be for A equal to A plus 1. So first you have to move A to register R0. Then you have to increment using simply INC A. Then you have to add the constant one, use hash 1 comma R0. For that you are adding 1 to A0. So then you have to move this result here, what it contains? A plus 1. So this can be moved to A. So move R0 comma A. Now here A equal to A plus 1. So this is the modified code by adding A equal to A plus 1 using single instruction INC. Now next design issue in the code generator is register allocation. So this is very important, the use of register allocation. So register allocation and assignment, deciding what values to keep in which registers. That is the use of register allocation and assignment. First, let us see these two are different: register allocation, register assignment. Register allocation, selecting the set of variables that will reside in registers at each point in the program. Selecting the set of variables that will reside, that will be placed in registers at each point in the program, that is called as register allocation. Whereas register assignment, picking the specific register that a variable resides in. Here it picks a specific register where the variable is placed or located. These are all the differences between register allocation and register assignment. Designed during the code generator algorithm. So we will discuss some more details about this register allocation and assignment. So now here, efficient utilization of registers in generating good code. So effectively, you can utilize the registers while generating good code. With this, what you have to do? Instructions with register operands are faster. Then store long lifetime and counters in registers. Then use temporary locations. Then even odd register pairs. So by considering these factors, so efficient utilization of registers in generating good code can be done. Now let us see one more example here. So in this example, two 3-address code sequences are given here. So that is for A, T equal to A plus B, T equal to T into C, T equal to T by D. This is one 3-address code sequence. Then another one B, T equal to A plus B, T equal to T plus C, then T equal to T by D. Both are different. Here first one A plus B is same. Second one is different. Here into is there, here plus is there. Third one by, divided by. So one operator is different here. Now you can see the shortest assembly code sequences for both the above code sequences A and B are given below. So here we will use R wherever R means that is register. Suffix R suffix I stands for register I. Now here we are using the instructions with simple starting letters. So for quick reference, now you can see for first 3-address code sequence, the assembly code is first. Here using different instructions. Earlier we used move, sub, add. Here other set of instructions we are using. First we have to load A to register R1. So for that we will use the command load L. So R you can use capital letters LOAD, load R1 comma A. So now A is moved to R1. So now what you have to do, you can add B to R1. For that now you can use A. That means nothing but capital A means add R1 comma B. So now what R1 contains? A plus B. Then what you have to do? Next one. So next one C is there. So now you can move here. M stands for move. Move C to R0. That is R0 comma C. So then what you have to do? Again you have to divide. So that with D. So T by D. So now here T into C means automatically. So here you will get A into B into C. Then that can be divided with D. So for that you can use D. So here D is nothing but divide. Divide R0 comma D. So what R0 contains previously? T into C, nothing but A plus B into C. So by D. Now that can be moved to the temporary T. So now here let us see store using store instruction. Store R1 comma T. Now we'll use another new register. So what it contains? So T equal to R1 here, the resultant value. So like that, we can generate the shortest assembly code sequence. Now similarly for B, here you can see A plus B. So load R0 comma A. Then what you have to do, you have to add B. So add so B to R0. So then again you have to add C to P, the previous one. So add R0 comma C. So then here we are using another new instruction, SRDA. So what is this SRDA? Let us see here. So shifts the dividend into R1 and clears R0. So all bits equal its sign bit. This is the use of SRDA instruction. SRDA R0 comma, let us say 32. So then here divide D R0 comma D, then finally store R1 comma T. So these are all shortest assembly code sequences for these 3 address code sequences. These are all just examples. How to write this code means during the code generation algorithm, there we will discuss. Now, next design issue is choice of evaluation order. So choice of evaluation order. So selecting the order in which computation are performed, then affects the efficiency of the target code. Then picking a best order, which is NP complete problem. So in the course formal language and automata theory, so during undecidability, so this NP complete and NP hard problems are there. NP complete and NP hard problems. So which are undecidable problem. So picking a best order, which is NP complete. Then some orders require fewer registers than others. So choice of evaluation order, so may consider the following factors or points. Selecting the order in which computations are performed. So whatever the order of computations. So in this order, you can select one choice. Then which affects the efficiency of the target code. Then picking a best order depends on the NP complete problem. Some orders require fewer registers than others. So this is the choice of evaluation order. Okay, now these are all the various design issues during the code generation, issues in the design of code generator. Okay, now our next concept related to code generation is the target mission or the target language. The target mission or the target language means that is the output. The output will be in which form? Absolute machine language form, then relocatable machine code, then assembly language. So it has three forms. So now how to represent this one? Various factors required for this. The target mission or the target language. The target mission and its instruction set is prerequisite for designing a good code generator. So the target mission and its instruction set, which are mandatory prerequisites for designing a good code generator. Use as the target computer a register mission that is representative of several mini computers. By using target computer, you can consider it as the target computer, a register mission that is representative of several mini computers. The target computer is a byte addressable machine with 4 bytes to a word, and n general purpose registers denoted as R0, R1 and so on, or n-1. It has 2 address instructions of the form. So OP, source comma destination. Here OP is nothing but opcode, operation code, opcode, or we may call it as instruction. So in 8085 microprocessor, in computer architecture and organization, so we know about all these instructions. So here OP stands for opcode, which consisting of source and destination. Where OP is an opcode, source and destinations are data fields, or we may call it as operands. So it has the following opcodes among others. So in our previous examples, we already mentioned some of these. So first is move. Here OP nothing but the opcodes are move, then add, then subtraction, multiplication, etc. These are all some of the examples of opcodes. So move, what is use of move? Move source to destination. Here whatever the source, that can be moved to destination. Then add, the meaning is add source comma destination, add source to destination. Whereas subtraction, subtract source from destination. These are all the meaning of the opcodes move, add, subtraction. So then in these instructions, various addressing modes are there. This concept also you studied in computer architecture and organization. Addressing modes are the addresses in the target code. Addressing modes also called as addresses in the target code. Target code is an assembly language. In assembly language only we will define or we will use various addressing modes. So the address modes together with their assembly language forms and associated costs are shown in the below table. The following table shows addressing modes along with assembly language code, then its cost also. This cost is very important during code generation. So we have to find the cost of the entire program. So by finding cost of each and every individual instruction, we have to find the overall program cost. So now first, what it contains mode. Here mode is nothing but addressing mode, the type of addressing mode, then its form representation, then address, then added cost. So now you can see first we are having absolute addressing mode, then register addressing mode, then indexed addressing mode, then fourth one indirect register addressing mode, then fifth one indirect indexed addressing mode. These are all the familiar addressing modes. So now absolute addressing mode simply denoted by M, capital M, then its address is also M, then its cost is simply 1. Why? Because for one memory location it uses. Then for register addressing mode, its form is register R, its address is also R. So registers won't take any cost. Why? Because those are all by default, so won't allocate any memory. So if anything you are using stored in registers, it won't take any cost. So wherever register is there, you can remember enter of this code generation, its cost is 0. Then indexed addressing mode using one constant of register. So C of R. This can be written as address, can be written as C plus contents of R. So first for constant C one location, then contents those can be stored in register R. So it takes only one cost, only for content. For register it won't take any cost. So for C it takes one cost, therefore cost is 1. Then indirect register using pointer R. So this can be represented in the form of address as contents of R. So here it is using only register, so it won't take any cost, therefore its cost is 0. Then indirect indexed, so using indexed C of R, for that indirect using pointer address, so pointer of C of R. So now for C it will take one location, for remaining in register it won't take any cost, so its cost is 1. Its address can be written as contents of C plus contents of R. Here in index already written C plus contents of R. For this now we are using indirect by using address. So like that, these are the various addressing modes and their formats and their addresses and their cost calculation. So during the code generation algorithm, so we will find cost like this. So now here in the above table, contents of R we used, what it represents, denotes the contents of the register or memory addresses represented by R. That is the meaning of contents of R. Okay, now a memory location in the above M stands for memory location M or a register R. Whenever a memory location is used means it takes cost as 1, whereas a register R user means it won't take any cost, the cost is 0. So a memory location M or a register R represent itself when used as source or destination. For example, let us see the instruction move R0, M. Here we used register as well as memory location. So which stores the contents of register R0 into memory location. So that means this is the source. Now M is the destination. Source is moved to destination. That means the contents of register R0 moved into location M. That is the meaning of this one. So now an address offset, capital here small c we used, which is the constant. What is that value? This is nothing but offset. From the value in register R is written as C of R. So now, for example, let us see one instruction. So move of 4 of R0, M. Here 4 is nothing but C. C equal to 4 here. So with the register R0, then memory location M. So which stores the value? Which stores the value here? So now here you can see contents of 4 plus contents of R0. First it takes 4 plus contents of R0. In the above direct addressing mode we used, so C of R means, so C plus contents of whatever the register used. So this can be stored into the memory location M. So for this the cost is, let us see, the cost is for memory location it takes 1, for the constant it takes 1. So therefore cost is 1 plus 1 equal to 2. For register you can't take any cost here. Wherever in assembly language code, wherever registers are there, we can't consider any code here. So now indirect version of the register and indexing modes are identified by the prefix asterisk. So move of star 4 of R0, comma M, which stores the value. Which value? Contents of 4 plus contents of R0. So this is a direct. So direct index addressing mode. Then whenever we are using pointer means indirect. So we have to use contents of. Again, outer side, one more address we have to use contents of 4 plus contents of R into memory location M. Then a final address mode allows the source to be a constant. So let us see. Now its addressing mode is literal is also one type of addressing mode. So previously till 5 addressing modes are there. So next one is sixth one is literal is also one type of addressing mode. It is of the form prefixed with hash followed by the constant value. Then what is the constant here? C. It takes only the cost as for constant only it takes one location. Its cost is 1. Therefore, thus the instruction move #1, R0. Here R0 won't take any memory. So only the constant stored in separate location. So loads the constant 1 into register R0. This is the meaning of move #1, R0. So then instruction cost. So in the previous example, so we mentioned how to find the cost. Here clearly see. So these same steps will be used during the code generation algorithm. So how to find instruction cost? So cost of an instruction is nothing but 1 plus cost of operands. So added cost in the table for addressing modes above discussed. Here you can see. Here we mentioned the costs, added cost. So by default, so 1 plus this added cost. Suppose 1 plus 0, here 1 plus 1, here 1 plus 0, like that. Based on the addressing mode, you can find the cost. So instruction cost is nothing but cost of an instruction is defined as 1 plus cost of operands. Operand cost can be obtained in the above addressing mode table. Then cost of register operand 0. We already discussed this point. So whenever you can use register, smaller or capital R, so its cost is 0. Then other than register operand, if a memory location, so 1 plus cost of that operand. Then cost involving memory and constants. So here memory M, constant C, cost is 1. So if wherever memory is there, that cost is 1. Wherever constant is there, the cost is 1. Suppose in one instruction both are included M, C. So then, for example, move M, C, let us say its cost is 1, for C cost is 1. Total 1 plus 1, its cost is 2. So like that cost is calculated. Then finally, cost of a complete program is sum of instruction cost. The instruction cost can be obtained with the register operand 0, with the memory and constant 1. Then generally cost of an instruction 1 plus cost of operands. Using these 3 forms, for every instruction separately you can find out cost. Then cost of the overall program equal to sum of all instruction cost. That is individual instruction cost. Now let us see some examples here. First, the instruction will be like this: move R0, R1. So that means copies the contents of R0 to R1, both are registers. Copies the contents of register R0 into register R1. This instruction has cost 1 since it occupies only one word of memory. So which stores the result? Why? Because whatever the R0 value, that can be moved to R1. So here registers are used. It takes only one cost. Then the store instruction is of the form. So move R5, M. Here you can see the contents in the R5 move to the location M, memory location M. Here register is there, then memory location is there. Now copies the contents of register 5 into memory location M. This instruction has cost 2. Why? Since the address of memory location M is in the word following the instruction. So therefore it takes cost as 2 here. For instruction, one location, then for the memory, one location. Therefore cost is 2. Similarly, the constant, whenever constant is used, the instruction is of the form add #1, R3. Now what is its cost here? So what is the meaning of this? Adds the constant 1 to the contents of register 3, that is R3, and it has cost 2. Or because for constant one location, then for instruction one location. Since the constant one must appear in the next word following by the instruction. Therefore, 1 plus 1, its cost is 2. For register, we can't take. For instruction one location, then whatever the operand value, it may be constant or memory. Then another instruction is of the form subtraction sub 4 of r0, comma star 12 of r1. Now here this is c of r1, c equal to 12. Here c of r0, c equal to 4. So now we have to subtract these two. So stores the value, which value contents of first 12 plus this one 12 plus contents of r1 from the destination. Source is subtracted from destination minus contents of this one 4 plus r0. So contents of 4 plus r0. Here c is 4, then here c is 12. Now here this can be stored into the destination. So star 12 of r1. Now what is its cost? Let us see here. Here we are having two constants. So it takes 1 for each constant. Then for instruction 1, for registers it won't take any cost. Therefore the cost is 3 here. So the cost of this instruction is 3, since the constants 4 and 12 are stored into the next two words following the instruction. So for this cost 1, then for this cost 1, for the instruction cost 1. Therefore cost equal to 1 plus 1 plus 1 equal to 3. So like that. So almost any assembly language program will be any of these 1 to 4 forms. Why? Because the following 5 or 6 addressing mode combinations. Then the cost will be calculated like this using these examples as base. Okay, now examples of code to generate for a 3 address statement is of the form we already mentioned. So a equal to b plus c, where b and c are simple variables in distinct memory locations denoted by these statements. Now you can see earlier we already mentioned a equal to b plus c. Now here try to find out cost also. Now the assembly code for this one form of the code, one representation. First we have to move b to r0, move b comma r0. So then add c to that b means r0. So add c comma r0. So then move r0 comma a. That means b plus c is moved to a. So this code we already mentioned above starting of this code generation. Now see how you can find out cost by seeing the above examples. Here b is one memory location which takes one cost. Then the instruction followed by the instruction, it takes one cost. Therefore cost equal to 1 plus 1 2. So we can't take cost for register. For instruction one location, one word. Then for b another location. So here 1 plus 1. Similarly add c comma r0. Register we won't take any cost. For c1 for this instruction one location. So 1 plus 1 cost equal to 2. Then move r0 comma a for instruction one location, that memory operand value a in another location. 1 plus 1 cost equal to 2. So for every instruction individual line wise costs are obtained. Then the cost of the entire program, total cost, you can add individual cost. Now you can see here 2 plus 2 plus 2, so 6. This is the total cost of entire program. Total cost of entire program. Like that you can find out cost of the program by finding individual instruction cost. The same code can be represented in simpler form. Now you can see here instead of more moves with only one move. So suppose here move b comma a. So b comma a. So directly we are moving b to a. So then you are adding in the buffer. In the buffer what it contains? A plus b. So now here what a contains temporary in place of register, it will use the memory location only. A contains a plus b, that can be moved to c. Now nothing but here c equal to a plus b instead of registers. Now here you can see the cost. So here we are having two memory locations. BA, here it takes cost 1 1. Then for instruction cost is 1. Total for this line cost is 3. Then for second line, here also one instruction cost is 1. For one memory location for C, another memory location for A, cost is 1. Here also 3. Therefore, 3 plus 3, 6 is the total cost. Why? Because here registers are not used. Different memory locations followed by instructions. That's why cost is differ. So assuming here R0, R1 and R2 contains the addresses of A, B and C respectively. So we can use the other representation by assuming the addresses of A, B and C stored in R0, R1, R2 respectively. Now you can see move pointer R1, comma pointer R0. Now second one, add of pointer R2, comma R0. Here the cost is C. For registers, here cost is 0. Here also 0. Only for instruction it takes 1 cost. So the first line cost equal to 1. Similarly for add cost is 1. For registers cost is 0. So the second line cost equal to 1. Therefore total cost, you will get to 1 plus 1. So this is the total cost of this program. So like that, these 3 representations carefully you have to remember. So further during code generation algorithm, so the cost can be obtained in this form only by considering these formats only. So now here, assuming R1 and R2 contains the values of B and C respectively, and that the value of B is not needed after the assignment, then we can use the other representation. Add R2, R1, then move R1, A. Here first line cost is only 1. Here registers are there, won't take any cost. So for first line cost equal to 1. Then second line move cost is 1 word. Then for memory location for A, 1 cost. For register it won't take any cost. Therefore cost equal to 2 here. Therefore total cost equal to 1 plus 2. So this is the total cost of a program. So like that, from the 3 address code, first what you have to do, you have to generate the assembly language code using addressing modes, whatever the addressing modes we defined combination. Then we have to find out each instruction cost. Then using the above combinations, then total cost by adding all the individual instructions cost, you'll get the total cost of the program. Okay. Okay. Now I stop here. So next class we'll come up with other new topic. So that is basic blocks and flow graphs that we will discuss in next.